Hello, folks, and welcome to Rational Science, the only site on the internet that does physics rationally. Everybody else does mathematics. They do a bunch of equations and give you the most irrational explanation they can find. Mechanisms. None of them work. None of them can be even imagined. They tell you they cannot be imagined, and everybody says, yeah, okay, we'll never figure it out. And nobody catches that. Nobody picks up on that. Everybody just believes what authority passes down to them. Anyways, we got a great day today. We're going to be talking a little bit about leaving the planet. People want to escape reality, so they want to look for ways out. One way is to go to Mars, even to the moon close by here. Another one is maybe travel on a gravity wave, subject of today. Okay, so let's go with our extinction segment. Let's see if we can escape the planet. Okay, let's find out about that. Here's some news that came out this week. Okay, and it's got to do with our expedition to Mars. Okay, it goes like this: 1 year on Mars, NASA analog astronauts begin mock red planet mission today, and you can watch it live. What is all this about? Well, they're preparing some people, apparently 3 astronauts. I think 4 are going to go. I don't know why they're preparing 3, but they're going to be sending 4 astronauts to Mars. 2 of them will descend on the planet and do their thing, and then they're going to come back. And that's going to happen, according to this note, anywhere between the late 2030s and the early 2040s. And the question is whether this is ever going to happen. Okay. Um, Says the round trip travel will be 500 days. Okay. That's over a year. 365 days a year. It's going to take about a year and a half, more or less. And that's just That's just going and coming back. Okay. And you can see some of the things they got to take. 25 tons of supplies and hardware would be ready and waiting for the crew, delivered by a previous robotic mission. And then they go over some of the problems that they're going to encounter, like gravity, which will be the biggest problem, right? Okay, so we're going to Mars, apparently. Will we? Will we ever get to Mars? And more fundamentally, why? Why do we want to go to Mars? I mean, here we have 4 people, apparently. They want to go to Mars, or they will be sent to Mars. Are we ever going to evacuate the Earth, 8 billion people, and move to Mars? Is that a possibility? Terraform, as Carl Sagan would say, terraform the planet. Okay, is that ever going to happen? Or are we just going to evacuate the jails, the prisons, and send all these people out there and say, well, we're going to send you out there to Mars? Okay. Who's going to go to Mars? Who's going to live in Mars? Are we going to start a colony like, when Columbus came to America, shortly afterwards, all the Europeans were coming to America, stealing land from the Indians, and doing their thing. Is that what's going to happen to Mars? For sure, I don't think we're going to encounter any Martians that are waiting for us, that we don't have to worry about displacing them or giving them bugs or whatever. But will we ever colonize Mars? And that's something for you to think about. Um, and these people are going to be doing something similar to what was done in the 1990s, I think 93, 94. And that's this Biosphere 2. I went to Biosphere 2 down south near Tucson in Arizona, and they had 8 people enclosed in there. Eerily, very much like the 8 mice with which Calhoun started his experiment, his mouse experiment. Anyways, they lived there, and apparently they divided up in groups, and they had problems with each other, and they did 2 experiments, and then they shut it down. And since then, they've been selling this complex from one organization to another. They haven't done anything else in there. I think it's just a tourist attraction now. That's about it. But they still have the place there for people to live if they ever want to do the experiment again. And the question is, this other one, the one for Mars, are they going to be doing the same thing? They're going to be putting these three people inside a place for over a year and see if they what kind of problems they run into. Both physical as well as mental, right? Because remember, these people are going to be traveling for over a year and a half, round trip, and so they want to try to figure out what kind of problems they might run into. And my question is all of this worth it? I mean, we might as well send robots, right, to Mars. Maybe more sophisticated robots, maybe R2D2 kind of robots that walk and do the things and lift things and so on. I think that's a better deal than sending humans down there. I mean, what's the point of that? Especially, to go lower them onto the planet, come back up, and come back home, like we did supposedly with the moon. Um, I don't know. I think it's kind of like a waste of um, uh, resources. And the question is whether as a taxpayer, would want to support such a venture, right? So these are things that people should consider. Now, in these projects, usually they develop a lot of technology, and that part's good. No problem there. But sending people out there, I don't know. Just the insurance on the lives of those people must cost a lot, even though they're taking risks. Anyways, they also have this project Artemis going to the moon, and I checked it. It says NASA's human lunar exploration plans under Artemis call for sending the first woman and first person of color to the surface of the moon. And yeah, I did check, and they're legal. They have a diversity and inclusion department. Okay, they covered that base. And so what I'm suggesting is that maybe they should send a trans person out there. That way they cover all the bases: men, women. Hopefully, this person is both Jewish and has a black father and a Chinese mother, and brother who is Buddhist. And that way we cover all the bases, and we don't have to worry about offending anyone. How's about that? Okay. That's my 5 cents worth on that. Again, I don't know why we're going to the moon, especially with people. Maybe we can send some robots that can do some excavating, some machines, and the robots handle the whole thing, and we can bring whatever minerals we need here on Earth. That I can understand. But sending people, what's the point of that? Are we ever going to live on the moon? Certainly, we can't terraform the moon because it's too little. We can't get gravity or air in there in the quantities that we would need. So we would always have to be, suited up and living in some kind of, house that we built out there for them, some place. And so here's my 5 cents worth on the moon landings for people who say, well, Bill, we never went to the moon, okay? And so, I kind of summarize here what the typical arguments against the moon landings are. Many people say that a lot of that was done in Hollywood. It could have been done in Hollywood. And my counter argument against that is, it's an invalid argument unless you can tell us the difference. If you cannot tell us the difference between doing it in Hollywood and the real thing, then you don't have a case. You can't bring that argument up. Only if you can tell the difference. Okay? If everything they did on the moon could have been done in Hollywood, you don't have a case. And they say, well, we saw this error and the other error and the other error. Well, I can tell you, if this was done in Hollywood, directors wouldn't have made so many errors, especially catastrophic errors. So the more errors you find, the more the weaker your argument is. Okay, so keep that in mind. Don't find more errors, because if you found one little error, that's one thing. But when you find 100 errors, then something's wrong with your interpretation, okay, about the physics up there. And some people think it's physically impossible to go to the moon. We can't go through the magnetism that surrounds the Earth, or the solar wind that hits us once we're out in space and so on. They have all these notions. I think a lot of that is just a misunderstanding of physics. And all I can say there, we built the ISS, the International Space Station. We built it in space. It flies around the Earth several times a day. We have satellites out there, for those of you who believe in satellites. And they have taken pictures of the Earth from outside the Earth. How did we get those satellites out there? And we have sent crafts to other planets and celestial objects. And so the question is, if we can send a craft all the way to the moon to go around it and come back, why couldn't we send a human inside such a craft? That's my issue there. And then the last one, people say, well, there hasn't been a mission since we landed on the moon. That was, 50 years ago. And the question there is, we never, and the issue that I bring there is that we had no need for one, okay? There was no need. It was a space race, essentially, and between Soviet Union, United States, and the United States said, "Hey, we got the gold medal. We got there first, no problem." But then, what was there to do after that? Build a colony on the moon? What would have been the purpose of that, aside from the expense? Tremendous expense. What are the profits? What's coming back? And the issue is nothing. It could be, some people might suspect and say, well, that was 50 years ago. Yeah, and where are we going now? Well, maybe we're trying to get some minerals, or explore the possibility of extracting minerals from the moon. I think that's the main one. Other than that, I don't see any purpose of going to the moon at all. Certainly not to inhabit the moon. And same with Mars. I mean, I don't think we're going to inhabit Mars ever. Maybe get there, yes. Back there, get there and come back. That I can grant it could happen. Stay there? No way. They're not going to be building anything out there and living there. Especially hundreds and thousands of people. No way. That's never going to happen. So the question is, why are we doing all these projects? Are we doing them to explore, to learn something about the solar system or whatever, if it's that important? I mean, there's a bunch of rocks around the solar system. So now we know everything we need to know. What else do we need to know about the solar system that is so important that we would spend money on sending people out there? So that's exploration. Are we going to do colonization? Are we going to really send people out there? And my answer to that is a flat no. And that's never going to happen. We might send someone up there, lands on the planet, comes back. That might happen, but live there, and start sending supplies and build a colony and expand? No. People are confusing Columbus with the logistics of what it would take to send someone to Mars. To the moon, we can even imagine that it's close by, but to Mars, a little more difficult. Okay. Anyways, here we have questions that people, or comments that people made since last time regarding autism and homosexuality. And these two people say the following. One says, the truth will come out soon. Autism is a vaccine side effect. And I think homosexuality is included as well. Okay, remember where you heard it first. Okay, thank you very much. Aren't you aware of the failure of the C-19 bioweapon injection? Oh my God, I wasn't aware that they were putting injections that are, what, bioweapons? Okay, and another fellow says, I think you should take school indoctrination into account regarding orientation these days. All I can say to these people is, they should listen first before they talk. I mean, I've said it several times. I'm going to say it one more time. I don't want to bore everybody who's been paying attention, okay? And here it is. Okay, here's Calhoun's experiment. This was done with mice. It was done first with rats, then with mice, okay? And the issue is the following. After a while, his mice, towards the end of the project, which lasted almost 2 years, they became homosexual and autist. Many of the mice became homosexual and autism. And a lot of them even lost all interest in sex completely. Okay, and so here we have animals. They were not injected with what, C-19, and they did not receive any indoctrination as far as I know. Okay, so that's one issue. The other one is here's this one. Let me remove this one. Give me a second here. And this is the other one that I showed a couple times now. Here we have lions, mounting lions, and sheep also doing it with sheep. male sheep with male sheep. And so the question is, this is in the wild. In the case of the lions, it's in the wild. Okay, the sheep obviously are under control of humans, but they're really out there in the pasture, etc. So they're in semi-wild, I guess you could say. But the point is that you have homosexuality among animals, and in the case of Calhoun's mice, you also had autism created or generated in the lab. And no vaccines involved, no indoctrination. You have to explain that before you go out and say, "Oh, it's school. It's what we learn. It's how this guy was taught at home and so on." No, it's like saying that a Down's patient was made that way at home by mommy and daddy. That he was okay until mommy and daddy, brainwashed him or whatever, or his school did, or his peers. No, that guy was born that way, and you got to explain that. And I'm saying that's got to do solely with genetics, okay, or at least most of it with genetics. If there's other factors, that's what can be discussed. But I don't think you can rule out genetics at all. Okay, what is it? I'm saying that we lost our genetic diversity. All humans are clones today. We have pretty much the same genetic structure. Despite that, we have mutations daily. We've had throughout history, right? Bottlenecks and founders effect, and here we are. We are all descendants of a relatively few that lived 100, 200 years ago. So if you go back in time, we are all more or less brothers and sisters in great measure because our great grandfathers, whether they were in Japan, in Africa, in the Americas, or Europe, it doesn't matter. They all went through the same sifting process with diseases. Diseases were the ones that they had to overcome. When they overcame those diseases, either by natural or artificial means, here we are. Okay? We are the descendants of those people, those who made it past the sifting process. Okay, that's why we're all the same. Okay, and one final issue here. A fellow says gender identity disorder was used for its diagnostic name when it was introduced into DSM-3 in 1980. With the publication of DSM-5 in 2013, gender identity disorder was eliminated and replaced with what? Gender dysphoria. Gender dysphoria is a handicapped mental disorder. And all I want to add to that is that, in 1973, that's 50 years ago, the American Psychiatric Association declared that homosexuality was no longer a disorder, a mental disorder, which it had been until that point. And that was a great victory for the homosexuals because shortly after they were able to change the laws and say that sex between men, especially those two, but also between women, was no longer a crime, which was until then was a crime in many states at least and around the world. And shortly after that, they just kept changing the laws. But the funny part is that they only in 1973 they only declared homosexuality not to be a disorder. They left all the other letters of the alphabet in the code, and everyone else was still committing a crime. Okay, so keep that in mind. Okay, let's move on to our subject of today, which is the gravity waves. What are gravity waves? Well, we've been talking lately about dimensions and contrasting them against coordinates and vectors, okay, and number lines especially. And so the question is, when you get into the subject of gravity waves, you have to include dimensions in your discussion because these gravity waves propagate through space-time, which is four-dimensional, and they are going to talk about two-dimensional, especially two-dimensional waves, right, propagating through four-dimensional space-time. So the word dimension is going to enter in there. So we can't get rid of it completely, okay? And then that's one issue. The other issue is fields, okay, because they had to create a medium through which these waves propagate or which vibrate and represent the wave that is reaching us. And so those were the fields. So we have two words there, dimensions and fields. And those are the ones that we need to use in order to discuss gravity waves. Okay, so here's what we've been talking about. We had these dimensions and coordinates. We put them under static concepts in our universal movie, and number, number line, and vector, they're at the bottom together with the dynamic concepts. Okay, what are we talking about here? We're saying the universal movie, you got to think of it as all we have at any cross section of the universal movie. You could say a cross section of motion, cross section of time. All we have is location. We have distance between every atom in the universe. That's all we have in a single frame. Next frame, every atom is now at a different location. That's all we have. So we have different locations of every atom in different frames. But in one frame, all you have is those static concepts. You have distance, location, existence, and you have the object itself. And for example, atoms, right? So where do we put 4D space-time? We can't really fit it in there, can we? In fact, they tell you that 4D space-time, four-dimensional space-time, is unimaginable. And partly because they're not talking about dimensions, they're really talking about about number lines. Okay, so that was the discussion in the past, a couple of weeks that we've had. Wormhole, what is the 1D? It's time. Okay, so the 1D in wormhole represents time. That's what a wormhole is. What does it connect? Well, it connects two zero-dimensional black holes, singularities. So at the ends of two wormholes, you have two zero-dimensional singularities, or black holes. And so what we have is really what mathematicians have been talking for ages, which is a line which is between 2 points. Okay, so that comes all the way from the Greeks. What are the points? Zero-dimensional, that's what they are. Geometries, you could call them. Geometric figures known as zero-dimensional, or that have zero dimensions. And you have the 1D line, which is the wormhole. So essentially what they've done is extrapolated these geometric concepts to their notions, mathematicians, right? Their notions of the universe, or how the universe really runs, okay, how it works. Okay, so why did I bring this subject up? Well, I was going to talk about this subject anyway, but it turns out that just by sheer coincidence this week, they had several pieces of news related to gravity waves. And here's one that I just picked up, okay? It says, astronomers across the world announced on Thursday that they have found the first evidence of long theorized form of gravitational waves that create a background hum rumbling throughout the universe. Okay, so turns out that they had already discovered these, as you see in the bottom line there. The existence was not confirmed until 2015. Yeah, they had already in 2015 detected two black holes colliding. Supposedly that's their theory, and that they were able to detect the gravity waves from that collision. And so the question is, what have they invented now? Well, the difference now is that this is a different type of gravitational wave. It's one that hums, that they can hear, okay? So I guess they turned it into music or whatever. And so they said it was done by many scientists across the planet, okay? First predicted by Albert Einstein. You always have to put Einstein in there because otherwise your paper doesn't get published, right? Turns out Einstein did not believe in gravitational waves, okay? So just keep that in mind. He wrote a paper against it and never believed in it ever again after that. More than a century ago, gravitational waves are ripples in the fabric of the universe that travel through everything at the speed of light, almost entirely unimpeded. Why would they be unimpeded? I mean, they don't bounce against planets or suns. I mean, there's all kinds of garbage out there, that in its way. Why would that gravitational wave reach us almost without impacting anything? Okay, so this is what that's one of the first issues we got to look at, right? But it turns out they say it was caused. They always, in order for it to be powerful enough to reach us, it has to be caused by a collision between two black holes, and that's more or less what it looks like. There you see it. Okay, so this came out. I think it was today. Two black holes colliding. Okay, and they have a million of these pictures. People love to see these things, and what you're staring at is idiocy, irrationality, complete irrationality. But people don't realize that. They say, "Oh, I understand. It's a little whirlpool there. They collide and they send shock waves outwards." That's all people understand, and they never question any of this. How this is really surrealistic. Okay, they have a zero-dimensional, two-dimensional, three-dimensional whirlpool there in the middle of four-dimensional space-time, which is really three-dimensional because, as you can see, the background is all just space and stars and everything that is three-dimensional. Okay, so just keep that in mind. It's all surrealistic what they're telling you, what they're showing you, and you're not listening to their words. They're saying 0D. That's how big a black hole is. It's 0D. It's no size, no shape. Okay, that's how big it is. It's infinite density. All black holes have the same mass. All of them have the same mass because the same density. Why? Because if the volume is zero, I don't care how much mass it has, the mass is going to be infinite. The density is going to be infinite. Okay, so all black holes have the same density. They should all weigh the same. Nothing, because matter has been crushed out of existence. Okay, but that's a subject for another day. And let me get this on the other side. Here it is. Here's another version of that. Two black holes, and you can see now the ripples through four-dimensional space-time. You see the four-dimensional space-time fishnet. Okay, and they say a subtle symphony of ripples in space-time. Astronomers use dead stars to measure gravitational waves produced by what? Ancient black holes. What are they talking about? Collision between two black holes. You can see the ripples in space-time. So what we need to look at is, what is that space-time? And, if they talk about just space-time, people say, well, time is a concept. What do you mean you're blending time with space? What sense does that make? And they say, no, don't worry. They're fields. That's what we're talking about. We're talking about fields. And so not only you get out of the dimensions into the world of fields, but they really both go together. You can't do without both when you talk about gravitational waves. Okay, so we had to research a little bit about fields. What are fields? Where did this word come from? What are they talking about when they say fields? What is this mysterious word called field? Is it a physical object? Is it a medium? That's the question, okay? Because supposedly the gravity waves are going to propagate through fields, or the vibration of the fields is the gravity wave. You can look at it either way, okay? So here it is, okay? This is the secret history of gravitational waves. Okay? You can find it in that magazine, American Scientist. It says, action at a distance disturbed fellow philosophers who demanded to know how gravity was transmitted from the Earth to the moon. Yeah, good question. Newton's celebrated reply was, hypothesis non fingo, meaning I have no clue. Such concerns gave rise to the notion of space-filling field. Okay, space-filling field. Okay, so they filled space with this field. The medium, okay, so field is a medium that transmits the message, okay, or through which the message is transmitted. You can look at it either way. So what is a field? It's a continuous and continuously varying plane of action. What in the world is a plane of action? Is that a thing? I mean, I don't know what kind of plane that is, but that's what they call it. The field is a plane of action through which disturbance propagate, eliminating the conceptual knot of action at a distance. Well, they haven't eliminated any knot. They just created a new knot. Well, all they said is that, there's this other concept called plane of action, and that's going to transmit, or through which the disturbance is going to propagate. By the 1840s, the creators of hydrodynamics were treating fluid properties, velocity, density, pressure, all as fields. Yeah, that's the issue. Today, no one doubts the reality of fields. Okay? So yeah, it's a done deal. They talk about fields, and what none of these people ever figured out is field is not a medium. It's not a thing. There's no such thing as a field. Field is a region. Okay, Region full of numbers. That's all. It's a mathematical concept. It has nothing to do with physics whatsoever. You can't use it as a paddle. You can't say a field did this, or the field vibrated, or whatever. You can't do any of that. Okay, here you have um, again, the breakdown here. You need the field and dimension. You need space-time as the box or sphere, the container within which we live. That's the official version. Okay, we live within this thing called space-time. So I asked the famous question, what's outside of space-time? What gives shape to the container? In other words, when you look at your right over there, what's the green stuff that either encapsulates the warp space time, right? Or the W map there, you know, the universe. What is outside of it? If space, time, and matter are all within these things, what's outside of it? That's what you got to tell us, you know. And of course, they say space-time is unimaginable because it is 4D, four-dimensional, right? If we can't imagine the 4D, much less can we imagine what encapsulates the container. So that's essentially your answer, okay? It's an unscientific question. We can't prove it. We can't, it's a philosophical question as far as they're concerned. So they never answer that question. On the inside of this unimaginable container, we have what? Math stuff. And here we have Stephen Hawking, okay, and he, as for those of you who know him, he was a mathematician who died a couple years ago, and he was like the king of black holes, okay, and so he knew everything about space-time, black holes, and all that stuff. Everybody just paid attention to him. And so what does he say? He says that space-time is made of points known as events. Here you see him. He says an event is something that happens. Okay? Yeah, an event is something that happens. But it happens with a particular point in space in a particular time. Okay, so we have a point which is zero-dimensional. Okay, and he's saying a point is the representation of a happens, of an event, of a phenomenon. Something that happened at a point. And so one can specify, well, with 4 numbers or coordinates. What are coordinates? He's telling you there. He's saying they're just numbers. That's it. All they're talking about is math. They're not talking about physics. It is often helpful to think of the 4 dimensions, 4 coordinates of an event of specifying its position in a 4-dimensional space called space-time. So what is space-time made of? It's made out of points. And essentially particles, if you want to call them, discrete little nuggets, grains of sand. In other words, space-time, they treat it as a sandbox, okay? And then he says it's impossible to imagine this thing he calls space-time. Okay, great. Okay, we learned a lot there. And then you find other people who say that actually space-time is full of energy, okay? Some substance they call energy, whatever that is. I've never seen it. I've never seen an illustration of this energy thingy, but everybody uses this word and says it's energy out there, okay? And then, of course, the fields. So what is inside space and what is it made out of? It's made out of all of these. And what they're going to be doing is using the fields, okay? The one at the last one there. That's what they're going to be using for the propagation of gravity waves. Okay, so let's see if we can make some sense out of all this. We have 4 dimensions, okay, and we're going to use the tesseract, which is alleged to be 4-dimensional. Okay, so here we have the tesseract, typical tesseract, little elongated on the sides, no problem there. Okay, and the first question we have is, what's the black stuff there? We need to identify that white stuff now, as you can see it there. Okay, what encapsulates the tesseract? 5th dimension? What is that? I need to know what material that is. What are we going to call it? Just the enclosure of space-time? And yeah, when you look up on the sky, we can't see the 4th dimension, but we can still see within 3 dimensions. And here it is, within 3 dimensions, we can see stars out there, galaxies maybe, especially if you got a good scope, okay? Okay, so that's what we see out there, okay? But these people put all kinds of stuff out there that they say fills this same 3D space, the one we're familiar with, right? And here's one. This one is the one proposed by Hawking, and that is particles. Okay, and he's saying that space-time is really made out of all these events, these uh, points. Okay, and this is the way they visualize them. Okay, and other people see it as energy. Okay, so you see this energy, this smoke, I guess. I don't know how to illustrate it because, nobody's ever really dealt with it in any way. Nobody illustrates the energy. We don't know what they're talking about, but everybody imagines it's some foggy substance. I guess that's moving out there. And others see space-time, all this ether that's in there, and they see the ether as waves. Okay, what are waves? The movement of ether. And yeah, they never got rid of the ether. They just changed the wording. They call it space-time. They call it whatever the false vacuum, whatever the words they use, but they all mean the ether. They haven't got rid of the particles out there. But those particles vibrate, and so they talk about waves. Okay, and so here it is. They see it as waves just crossing uh, our 3D world, the 3D universe, the one we can see. Okay, we can't see the 4D. Okay, okay, so, but what are waves made out of? Okay, because we want to get to the bottom of it. These waves are flowing. You can think of them as gravity waves as well as light waves. And one of the things they're trying to do is trying to see if they can merge light with gravity. Okay, so that's so you can imagine that gravity waves might also be transverse waves. Okay, but typically they think of them as longitudinal waves. Okay, but what are these waves made out of? Well, they're made out of fields, as we just said. Give me a second here. On the other side as always. Okay. So what are they? Well, they're vibrating fields. That's what they say these are. Okay, so that's what the waves are made of, fields. In fact, transverse waves are made out of two mutually orthogonal fields. Okay, so this is where we're at. We've got space-time, four-dimensional. We cannot imagine, we cannot see it. Fine, so we don't do that. But in our 3D world, they say we have to detect whatever's coming to us. And they say we've detected these, I guess, two-dimensional waves, transverse waves or longitudinal waves that are coming from the collision of two black holes, and we detected it with these sensors that we have here on Earth. Okay, that's essentially the pitch, the sales pitch. Okay, and that's what you're paying all those big bucks for, in tax money and so on. Giving it to these guys. Okay, so here's one of the gurus today, and he tells you right in your face that everything is fields. Everything is made out of fields. Okay, here it is. And his name is Sean Carroll, and he gave a talk at the Royal Institution, The Particle at the End of the Universe. He says, to understand what is going on, you actually need to give up a little bit on the notion of particles. Instead, think in terms of fields. Aha, so that was the secret. When you hold two magnets close together, you can feel their attraction or repulsion before they even touch. An interaction between two magnetic fields. So we have interaction between fields, okay? So we got to figure out what these, baseball bats are called fields, okay? How they interact. Likewise, when you jump in the air, you're going to come back down. That's because you live in Earth's gravitational field. So this field apparently has some powerful influence over you. You jump, and brings you down, and you can find, the fields are pulling two magnets together. Okay, so we need to get to the bottom of what this field is, because it's this field which is going to be coming with a gravity wave. The gravity wave is going to come through a field, or it's the vibration of the field itself. So we no doubt about it, we got to get to the nitty gritty here and find out what a field is. What is a field? And here this fellow tells us, he says, he tries to get rid of Newtonian action at a distance. He says there really is no action at a distance. Instead of just thinking about random forces between objects very, very far away, imagine there is a field filling the universe. Okay, whatever a field is, it fills the universe. And what does it mean? He says, what that means mathematically, not physically, okay, mathematically, is that at every point in space there is a number. So what is a field? Well, it says that at every point in space there's a number. He's talking about a region where you have values. It says, in fact, it says the value of the field, just like the temperature of the air in this room. At every point there is a value, the temperature at that point of the air. So what he's saying is that a field is just a region with a bunch of values that have different strength, or different, in case of temperature, different temperatures or whatever. So in the case of gravity, it would be different strengths of the gravitational so-called field. So all he's done is give us a description. He hasn't told us how a field does this magic. He just says, look, if you're over here, you're going to have so much strength from the field, gravitational field. If you're over here, you get more strength. Over here, you get more strength. Okay, that's all he's saying. There's different strengths at different locations. Okay, not very useful. And then he gives us his punchline, his corollary. Okay, he says, look, gravitational force is the slope of a field that pervades space. In other words, far away you have the potential field is very weak, and as you approach, say, for example, the Earth or a planet or whatever, celestial object, it just gets stronger. Okay, and that's all he's saying. All he's talking about is strength of a field. He hasn't told us what a field is. In fact, he has told us, he says, a bunch of numbers, a bunch of values. And certainly we cannot pull with values. We cannot pull with numbers. We cannot pull with kilograms or with whatever, whatever pounds, whatever you want to use here. You can't pull with pounds. You got to explain how you pull. Okay? And you got to explain the physical mechanism. And he hasn't done that. All he's done is describe, says that it's stronger over here than it's over here. Okay, so he hasn't told us. He just measured, gave us a value, and he says that's the way it is. Yeah, okay, that's the way it is. You haven't told us how that happens, by what mechanism. Okay, what's the cause? And that's what physics is about, not measuring and give us a value and saying that it's stronger over here than over there. Okay, great. It's hotter over here than it's over here. Like you put your finger in the boiling water and say, hey, it's hot. It's hotter than out here. Yeah, okay. So what have you told me? Can you tell me why it's hotter? That's what we want to know. Not to tell me, oh, over here it's cold, and when I put my finger in the boiling water, it's hot. Great. What do you give you? A Nobel Prize for that? Okay, so here's the Caltech version. Okay, we have these black holes, and they send out all these waves. Okay, just by their motion. And here we're not talking about the collision of two black holes. We're just saying that the black hole sitting in space-time, right? Just bending this, sandbox, somehow sends gravitational waves to us. And these are two-dimensional waves or longitudinal waves that are reaching us and that we can detect. Okay, and there you see the waves. Okay, these are illustrations from them, not from me. I just borrowed them to show you what they are proposing. They're saying, look, there's these waves, and they're coming to us. And how were they generated? Well, they were generated when the black hole pushed down the sandbox. You have a ball, baseball maybe, a bowling ball you want, okay, bowling ball in a sandbox. Pushes down, and somehow it creates a ripple through the sand that comes all the way to you and pulls on you. Okay, let's get that straight. It's going to pull on you because it's gravity, and gravity is a pull force. It's an attractive force. It's not a repulsive force. Okay, it doesn't push you away. It's supposed to bring you inwards. Okay, like a cowboy pulling on a rope that's tied to a donkey. You pull the donkey forward. You don't pull like that, and the donkey goes farther and farther away. It's the other way around. Okay. Okay, so here are two ways of looking at this. Here you have a ball sitting in the sand, and it's going to cause this gravity well. Okay, this is what they're proposing. Okay, and here you have the ball is going to fall through that gravity well. Okay, it's going to make, you can see it falling through there. And the question, does drilling through a sandbox, okay, does that cause ripples along the sandbox, along the sand, that pulls all the other balls inwards towards it? Or, first, does it attract them? And second, do the ripples travel through, the sand? Those are two questions you got to ask, because that's what they're saying space-time is. What was space-time? Well, it's a field. And what is a field? Value at each point in space. And what did Hawking say? It's just events, points. So he's talking about a sandbox, and somehow, because this black hole, which weighs tons, infinite weight, no problem, we'll concede, it weighs down the sandbox, and somehow that produces ripples that not only go outwards, but pull you inwards. That's the mechanism. So what sense does any of that make? I don't know. That's for you to figure out. Okay. Okay, here we have the situation. We have a ball pushing down space-time. How does it attract another ball? I mean, we can imagine here, like, you can't imagine the pull mechanism at that point, but if you remove that hump, okay, we're going to remove the hump. Now we can imagine, simply because of gravity, one ball rolling towards the other. But we cannot imagine this if that hump is still there. Okay, so the issue is, if you put a ball, a bowling ball, in the sand and sink it in, you can step on it and push it in all the way as far as you want, okay, down the rabbit hole, okay? Does it pull on does it send ripples through the sand, first of all the grains of sand moving all the way to the tennis ball that's on the other side, and does it pull it inwards? Okay, and so that's for you to figure out if that's the case. Okay, and here you have two black holes going around each other. They're going to collide eventually because of their gravitational attraction, supposedly. But what they send out are these ripples. And they're saying that it's like, if they were in the water, like two stones rolling around each other in the water, and they send all these ripples outwards. Okay, we can concede all that. Let's assume that's the case. How does that produce attraction? Assuming this is the case, all the ripples go outwards. How does that attract you? Okay, here I'll give you another version or another analogy. Here you have sound. Okay, someone speaks. It vibrates all the air around him. Okay, and the sound waves go outwards. Okay, so you have all these actually longitudinal waves moving outwards from the speaker, radially outwards. How does that pull you inwards? What is the mechanism by which it pulls you inwards? That's the question. Okay. And here you have in a similar situation, you have the water waves, okay, and they move from left to right here, okay. And so the question is, how does that attract you if they're going in one direction? So that's what we have to explain, because the gravity waves are coming towards us here on Earth. They're coming towards us. I cannot imagine how that pulls you, especially if they're waves. And then we get to the nature of a wave. What is a wave? Well, a wave is made out of fields. And what is a field? Well, the field is made out of vectors, as we covered that in the past, okay? And here we have them, okay? Here's a dissection of the famous electromagnetic wave, okay? It's made out of two fields, one they call the electric, the other one the magnetic field. And the question is, what are we staring at? Well, what we're staring at is a bunch of arrows, blue arrows and red arrows. So what are them arrows? Engine arrows? Well, those arrows are vectors. Okay, that's what they are. They're magnitude and direction. The arrow stands for direction, and the height of the arrow stands for the magnitude. That's what you're staring at. And this is more or less what they're saying that gravity waves or gravitational waves are. More or less like electromagnetic waves. Okay. Now, some visualize them as transverse waves, that propagate up and down and sideways, perpendicular to the direction of travel, meaning as they come to Earth, okay, you can visualize them as going up and down and sideways. And that's one way of looking at it. The other one is as a two-dimensional, or really a one-dimensional longitudinal wave, which is back and forth. Okay, so you can look at them, or a mixture of both. Okay, but what are we staring at? That's the important part, because what we're staring at is a so-called wave that is made of fields, two fields in this case. Each field is made of vectors, which are just magnitude and direction. And so what is a field? Just a bunch of moving vectors. All we're talking about is math so far. We have no physical object. What is a wave? Two waving fields. Again, we're talking about math. None of this has anything to do with physics. Okay, all those are descriptions, mathematical descriptions. That's all they are. And that's all they can do because they're interested in the numbers and the values. They're not interested in visualizing what physical object could be out there in the invisible world in which Mother Nature operates. Okay, so where do we put these longitudinal or transverse or both uh, gravitational waves? We have to place them somewhere. Well, we have to put them both wave and the field of which they're made. We have to put them in the dynamic section at the bottom. The ones on the top, they only occupy a single frame, the yellow one there. The beige one at the bottom, that requires at least 2 frames of the universal movie because you're talking about motion. Okay, what is motion? 2 locations. Okay, location, 1 frame because it's just a set of distances. Motion, on the other hand, requires 2 locations and therefore it requires 2 frames of the film. And so both wave and field of which the waves are made, whether they're transverse or longitudinal, they are dynamic concepts. And in fact, we have a problem here because they treat them as physical objects. They think that wave and field are both physical objects. As you saw Sean Carroll, he says particles, they're made of fields. What are these fields? Are they nails? Rocks, plants, what are they? And he tells you, he says, no, they're numbers. That's what they are. In fact, the word field came from Michael Faraday, who in the 1840s, I think that's when he coined the term. He probably used it even before then, but that's when it first appears in the books. And what did he say? He said, look, it's a region where something is moving, okay? And he called those lines that you see when you put a magnet and you see all these little lines, lines of force, as he called them. He said, look, those are made of matter. The line itself, not the particle, not the iron filing, but the fact that they align, he said, along something that is physical. And then Maxwell came a few years later and he said, look, there's matter in motion. That's what those lines of force, that's what a field is. It's made of motion of something, of some matter. So a field is a dynamic concept. Okay, there is no, I can't bring a field and put it on the table, partly because, you can't bring a field, that's one issue, but you could make a mock-up of it. But the problem is that a field is something in motion. Okay, something is moving in that region. That's what people don't always understand. And that's why I always like to show that, I prepared that today, but I like to show how if you put a magnet underwater, it collects 1 iron filing at a time. You can see all the iron filings slowly going towards the magnet because something is moving in that region we call field. Field is not a static concept, not a static object that I can put on the table. Field is something in motion. You have to identify the something that is moving in there. And only then can you talk about gravitational waves coming towards you and saying, look, it's a field. Yeah, but what is the field? What is it that's moving? What is this vibrating thing that I'm detecting with all these sensors? And that's what they never identify. So they say it's space-time, it's field. They use all these concepts just to get you out of the way, but they never identify the physical objects. And that's the whole problem with, gravitational waves. We still don't know what they are. Okay, we're going to get to some of the questions, comments people made. One fellow says, space is not nothing. Space is not nothingness. Just because you can't see ether, energy, electricity, magnetism, gravity, it doesn't mean there is nothing there. Well, yeah, I mean, we got a problem here because we can't see or touch, really the energy because it's a concept. Gravity, it's another concept. You cannot see magnetism because, again, you got to identify the thing that is doing the magnetism, the gravity, and the energy. There's something there that's doing these things, but see, this fellow thinks that these are things, and what they are is mathematical concepts. This is what has not entered his brain. He doesn't realize that these are all abstract mathematical concepts, and they've never identified the objects that do energy, that do gravity, that do magnetism, or electricity. That's what you got to figure out. What object is doing these things? And if you say, look, there's no object because I can't see or touch it, then you're doing it with black magic. You're doing attraction between two magnets, right, as I always show. You're saying that magnetism is happening because there's nothing here, absolutely nothing, because you can't see or touch it, and you're saying there's nothing there. If there's nothing there, your explanation for this phenomenon is black magic, is based on black magic. You're doing witchcraft, not science. You have to put an object in there. You have to visualize it and explain it for the audience that there is a physical object in that region that you cannot see or touch, but you're going to explain the mechanism of how one magnet attracts another. And there had better be a thing in there, okay? But space is something else. Space is not an object, it's not a thing. So for that, you need to define what a thing is. You cannot say it's not nothing until you define what nothing and something is. First you define these words, then you can say that, okay? Right now, you still haven't defined them. Okay, another fellow says, space is zero-dimensional in a three-dimensional continuum containing positions, directions, and distances. Okay, well, 0D, if space is zero-dimensional, can't be in anything. You know, you can't contain the zero-dimensional nothing. And that's the first one. So you cannot contain it. So your wording is wrong, okay? Then it continues, says continuum is not a thing. You know, he says it's a three-dimensional continuum. No such monster. Continuum is not a thing. You can't say it's three-dimensional like you say three-dimensional table. You know, you can't say three-dimensional continuum because continuum is a concept. You got to identify or draw the continuum. You know, what is this three-dimensional continuum? Okay, draw it. Because if it's an object, it's got shape, you should be able to draw it. Okay? And therefore, continuum is not 3D. You cannot say that continuum is 3D. And then in physics, things can't contain concepts. So you can't say that this concept called continuum contains positions, directions, and distances. Those are all concepts. You cannot contain them. Okay, so fail on all counts. You got to work a little harder on your assumptions, okay, on your definitions, etc. And I think it's the same fellow who says the following: 3 dimensions, height, width, and depth. No, depth is not a dimension. Depth is a vector. Okay, and there we have it. Okay, right at the bottom. Okay, dimensions are known as length, width, and height. Okay, no depth there. Depth is motion. Okay, and you have the 3 coordinates there, but depth is motion. So you have depth, breadth, and elevation. Those are the 3 motions. Vectors are motion, displacement. Okay, in 3 mutually perpendicular directions. That's what a vector represents. And mathematics doesn't use any of these. Mathematics just uses number lines, okay, as we discussed in the past. Okay, here we have another fellow says, a square is a shape itself. The word shape is a concept in the dictionary. Okay, true, yeah, we agree. So a thing that is only a concept itself cannot be an object. Okay, and where did he get that? I don't know where he says that shape is the same thing as object. No, it's not. This is why objects have to be have more meaning to them than only have shape. No, shape and object are not synonyms. Okay, sometimes we use them interchangeably, but they're not. Shape is a property, an attribute, you could say, of an object. Okay, so it's like this is the qualifier, and we call them adjectives in physics. So in physics, an object is a noun. You can say the table has shape. Okay, what are we saying there? We're saying the table is the object. Shape is an attribute that it possesses. Okay, and so we call things or words such as shape, we call them adjectives. They're not nouns in physics. Okay, so we have a new language, folks, and unless you are in tune with the language, you're lost. The word motion, the word orbit, you know, they are not displacement. None of those are nouns, not in physics. All those are verbs. Okay? So you can't say the orbit. No, the orbit means that you're treating orbit as a physical object, okay, in physics. In ordinary speech, you can say whatever you want. Okay? You can say love is an object. You can say love exists. In physics, you can't say that. Only objects can exist, and so on. So you got to get in tune with the language. Okay? And right now, a lot of people are having problems with the language. Yeah. Until you get in tune with the language of physics, you're going to be lost. Okay, another fellow says, objects are forms, not shapes. Uh-huh. Because shapes are two-dimensional representations. Forms are three-dimensional. Well, um, in German and in Spanish, okay, at least those two languages I can tell you for sure, there is no word for shape. That word doesn't exist. They just call the whole thing, whether it's two-dimensional or three-dimensional, they call it form. So just be aware of that. Shape is a word that was invented in English, and we don't care what it's used for. We're saying that in physics, we're just looking at the outer region of an object. And the object, we don't make any distinction between three-dimensional and two-dimensional objects when we talk about the definition of the object. We're saying it has to have shape, and for that, all we're looking at is the outer, what we can see there, or what it has. Even it doesn't require an observer. What it has on its own. And in the case of a square, it has a shape on its own, whether you look at it or not. Okay, it could be the face of a cube, and we call that a square. And that square has shape all on its own. It's two-dimensional. You want to use form? I don't care. Shape and form are perfect synonyms for the purposes of physics, especially for the definition of the word object. So there's no difference between one and the other. And then the other issue there is that, we don't have to define the word shape. Okay? Some people say, well, define the word shape. Those are devil's advocates, extreme devil's advocate, who just want to win the discussion. We're not interested in winning the discussion. We're trying to get a definition of the word object because we cannot do physics without objects. So it's the first word we have to define in physics. Probably next or second word after the word definition itself. You need to know what a definition is. Then you can move to the word object. But you need to define the word object because you cannot give a physical interpretation, a mechanism, without the word object. So you need to know what an object is in physics. And right now, people use the notion that an object is that which you can see and touch. And that's an irrational definition. You need a second object to see or touch. We can't see or touch all the objects in the universe, especially those that are on the other side of the universe, right? Can't see or touch them. And people say, well, but it's got the possibility of being touched or seen, and you can't say that because you haven't done that. You haven't tried to touch or see it. So we don't know if you can touch the table that the Klingon has on the other side of the universe. And you say, well, let me try it. Let me do the experiment. No, we're not going to let you do the experiment because we don't define words through experiments. And that's the problem. Okay, so you can't say that the moon is not an object until the asteroid touches it and hits it, No, you can't do that. Hopefully the moon is an object before the asteroid touches it. Okay, so yeah, the moon is an object because it has shape, not because the asteroid can see and touch it. Okay, another fellow put a comment today. He says, why assume that gravity is a pulling force rather than a pushing force? Is it because you can't push on a rope? Well, you got that wrong as well. A ball, that's what they use in quantum mechanics, can only push. There's no way you can pull with a discrete ball or particle or whatever. A rope, on the other hand, can both push and pull. You push through a rope by torquing it. And all I can do is say, grab a rope, your grandmother's rope, where she hangs her clothes, and tie it to whatever on one side of the wall and on the other, and just torque the rope, and you'll see that there's a thump at both ends. Okay, the signal presses on both atoms located at the ends. So yeah, a rope can push, not by shoving it in one direction or the other, but just by torquing it, which is the mechanism we're proposing. Anyways, here Richard Muller, from Berkeley, he tells you that all atoms on Earth pull on each atom of you, and you pull on each atom of the Earth. He says, so for example, if you have the Earth, there's a big mass here, and you have you with your little mass here. Every atom on the Earth is what? Pulling on every atom of you. You're also pulling on it. Okay? So, yeah, you have to explain pull, not push. You can't explain gravity with push, like some people out there attempt to do. And good luck with that, because the way they produce it with push is you could say the Casimir way, which is you remove the particles between two objects, and whatever particles are on outside of it, push them together. That's the way they produce pull with push in Ptolemaic way, you could say, a roundabout, irrational way. Now, gravity is a pull force, okay? I mean, it's an attractive force. You got to explain the attraction, how that attraction happens. And that's what we do with a rope, because it's an extended object. And the only force you will not find in all of quantum mechanics, in all of mathematical physics, is the force of pull. They never invented the force of pull in mathematics. Why? Because they never discovered what mediators Mother Nature uses to do her daily work. I'll see you next Sunday. Bye-bye.